Hey guys, it's Miss Buck. I'm going to do a quick video for you just because I want to be able to explain this topic to you a little bit. I'm going to put the link for just the straight Google Slides presentation right below this. So you're welcome to get your notes. Either you can pause the video as you're going through it, or you can listen to the video, answer the questions I have embedded, and then you can look at the Google Slide presentation, whichever way you like, okay? All right, acceleration is really the first topic we get into that kids start having a little bit of trouble with, okay? So I have two sons, and to get us ready for this topic, I was trying to think of a good example for you of acceleration. And both of my sons love anything that has to do with cars or planes or I don't know. They're always doing stuff. Anyway, I know when they were younger and they would talk about a certain car, they love to talk about things like this car can go 0 to, I don't know, 80 miles an hour, 0 to 100 miles an hour in so many seconds. Well, what you're talking about there is acceleration. What you're really talking about is how fast can something speed up or slow down? Or in the case of physics, how fast can something change direction? Okay, so we're not just talking about that a car can go 150 miles per hour. That's cool. But how fast could it go from 0 to 150 miles per hour? That is acceleration. So in your notes, you want to go ahead and write all of this down. Acceleration is going to measure the rate of change in velocity over a period of time. So remember, like a car can go 0 to 100. That's the change in velocity in, I don't know what a good time would be. 10 seconds, is that good? Over a period of time. Now, this is where it gets weird. Most of the time in everyday language, when we say something's accelerating, we mean it's speeding up. In physics, acceleration can mean something is speeding up, but it can also mean something is slowing down. We talk about a negative acceleration. And it can also mean something is changing direction. This is the one that's going to get you. See that one in blue? It's going to get you on the test. You've got to remember in a physics classroom that acceleration can also mean that something's speed is staying constant, but it's changing direction. And so we would say that it's still accelerating. We want you to add this doodle to your notebooks. I can't draw well either, but this is a pretty simple doodle. At the top, the little stick figure is accelerating because it's speeding up. In the middle, it's accelerating because it's slowing down. And then your little bumblebee looking thing there is accelerating because it's changing directions. Add this to your notebook. You don't have to write anything here, but I think it's just a really good example to help you get the right mindset. I don't know how many of you are already starting to practice your driving or been around in a car. Can't get my pen. But when you drive, you've got inside your car, you've got your gas pedal, right? And when you push the gas pedal, you go, you move, you speed up. So that would be an accelerator. You also have a brake pedal. So you hit the brakes when you want to slow down. Well, in physics, that is also an accelerator. And then you've got your steering wheel, right? You've got your steering wheel, and that makes you change direction in a car. In physics, we would also call this an accelerator. So speeding up, slowing down, changing direction. Let's see what happens if I do that. Oh, that's pretty good. See if I got it. All right. All right. Here's where it starts getting tricky. Excuse my coughing and stuff. I'm still working on getting better. Okay. We know that velocity is a vector. We have to draw an arrow because it includes a direction, right? The tornado is moving at 10 miles an hour east. Well, I would draw my arrow pointed east. And remember, the larger the vector, the longer the line, that is telling me something about magnitude. Okay, so a short little vector is a smaller magnitude, a longer vector is a bigger magnitude. All right, well, if velocity is a vector and acceleration is telling me how velocity is changing, am I speeding up or slowing down? Then that means acceleration also has to be represented with a vector. This will just take practice, guys, and that's what you'll be doing tomorrow. You are going to just practice looking at these different representations of acceleration and figuring them out. And it just takes practice. It's like anything else. But for now, I want you to reproduce all this in your notebook. So if there's some object up here and it's going, there it is, that's its speed, right? It's going 100 miles an hour. I don't know. We'll just say it's going 100 miles an hour. If the acceleration vector is pointing in the same direction, then that means this is going 100 miles per hour, but I also know that it is speeding up because the acceleration vector is pointed in the same direction. It's speeding up. If I have an object in motion and the acceleration vector is going in the opposite direction, this tells me that whatever object this is actually slowing down. It's still moving. It's still in motion. I know that because I see the velocity vector, right? But the acceleration vector is going in the opposite direction. So that tells me this object is slowing down. Yes, here comes some math, okay? And you won't like it. You're going to fuss at me because we're going to make you write it all down. But we do think it's important that you have at least one example in your notes of how to calculate acceleration, okay? All right, so we've got our little roller coaster thing here. And right over here at the top, it's telling us that when it hits the top, it's going 20 meters per second. Now it's going to come around, it's going down, and it's speeding up so that its speed when it gets to the bottom is 40 meters per second. Now this is just speed, right? 20 meters per second, 40 meters per second. You're going to see that a lot of times we're going to use the words speed and velocity interchangeably, all right? I know that technically this is velocity with a direction component, but the magnitude part of that is just the speed, all right? So if I want to know the acceleration, that means I want to know the rate of change at which it went from 20 meters per second to 40 meters per second, okay? I want to know how fast it did that. Then I'm going to use this equation, okay? Average acceleration equals, this is weird, the final velocity, what it was going down here at the end, minus the velocity when we started, divided by how long it took to do that. So there's the, yes, I want you to write it down, quit moaning. At the top of the hill, a roller coaster is moving 20 meters per second. It increases in speed to 40 meters per second. If it takes 4 seconds to reach the bottom of the hill, what is its acceleration? So it went from here to here in 4 seconds. So here's how you would do it. 40 meters per second minus 20 meters per second. 40 minus 20 is 20, divided by the difference in time. How long did it take to do that? It took 4 seconds. 20 divided by 4 is 5. Now here's where we start having a whole lot of fun. Look at the unit. It's 5 meters per second squared. Let me explain what that means. It's what that is saying is that every second the roller coaster went 5 meters per second faster. Every second the roller coaster went 5 meters per second faster. And so acceleration is going to have, instead of saying 5 meters per second, we just say 5 meters per second squared. Okay, so I want you to write this down, just right underneath the problem. Go ahead and write this. Okay, this means that each second the roller coaster is going 5 meters per second faster. Because try to keep in mind, acceleration is telling you how speed is changing over time, whether it's speeding up, slowing down. We won't do a lot with changing direction in 8th grade other than just to know it. So I made a little data table so you could see. At the top of the hill, it's going 20 meters per second. If every 1 second is going 5 meters per second faster, then 1 second later it should be going 25 meters per second. 2 seconds after it starts at the top of the hill, it should be going 30. 3 seconds after the top of the hill, it should be going 35. And then you can see 4 seconds later, when it gets to the bottom of the hill, it's going 40 meters per second. So acceleration is measuring this change over time. You can add this or not. You can also just stop and see if you could figure it out. Like you could pause the video right now and see if you can do it all by yourself, because I'm going to ask you, when Sarah ran a race on a straight track, her speed changed from 3 meters per second to 6 meters per second over a time period of 3 seconds. What was her acceleration? Here's the answer. Here's how you would set it up. Final minus beginning, that's 6 meters per second minus 3 meters per second, divided by the time. 6 minus 3 is 3. 3 divided by 3 is 1, but did you get the unit right? Meters per second squared. Every 1 second, the acceleration is changing by 1 meter per second. All right. Sorry about the coughing, guys. We will practice with the acceleration graphs a lot. But one thing that they're going to ask you on T and Ready, and that we will be asking you, is we will be giving you these graphs, and we expect you to be able to tell us what's going on. The biggest issue is not to get them confused with each other. We have just spent a bunch of time doing this. We've been over here doing these distance time graphs, right? We know this object's moving away. Now it's not moving at all. Now it's continuing to move away. The steeper the line, the faster it's moving. Okay, well, we're changing. And now look at how it's labeled. These are velocity time graphs, not distance time graphs, velocity time graphs. Now, I'm going to tell you something. A lot of times, instead of the word velocity, sometimes you'll see this a speed time graph. Okay, so again, a lot of times we will just call it a speed time. We really know it's velocity, but we'll just call it a speed time graph. It's different. You have to stop and look and see which graph you're dealing with, or you're going to miss the question, okay? All right. This is not highlighted in yellow, but do you see how I put a red box around this? You definitely need to write this in your notes. I would kind of add this right below it too. All right, these are speed time graphs. Here we go, see, over here, speed. All right, on a speed time graph, if you have this straight horizontal line like this, that means whatever object we're looking at is going at a constant speed. It doesn't mean that it's not moving. And one thing that I always tell kids, and it helps me a lot, is to just add some numbers in here. Okay, not doing very well, but it's okay. So if I just add some numbers in here, then it gets super easy, okay? We'll say that that represents 5, not as good as the Khan Academy guy. There's 10, here's 15, and here's 20. All right, so I don't know what this is, but it's some object, okay? It's some object. So now it looks pretty easy. Whatever object this is, time is changing, it's going on, but look, the object is going 15 miles an hour, 15 miles an hour, 15 miles an hour, 15 miles an hour. So now you can see if you just slow down and look over here, speed versus time, that speed, just telling you the speed is staying the same right there, okay? Whatever object it is. All right, remember I'm looking over here and seeing that this is a speed time graph, not a distance time graph. So on a speed time graph, now this line means whatever object is there is speeding up. And again, guys, just add some numbers and it'll be super easy for you, okay? So again, if this is 10, 20, 30 meters per second, miles per hour, whatever it is, now it's easy to see, oh, this object is speeding up. Same down here. This graph means whatever object it is. I don't know, let's say it's 100 miles per hour over here, and now it's slowing down. So this makes sense because acceleration can be speeding up, slowing down, or changing direction. I think really the better way to describe slowing down is negative acceleration. I don't think the physics teachers at DB really like that word decelerating. They'll let you know when you get there. I think they like negative acceleration because you'll deal with negative numbers when you get up there. All right, so let's compare two objects. So again, when you have both of these, they're both speeding up. I know that. It's a speed time graph. They're both speeding up. This one, now the steeper line means that this one got to whatever speed it is a whole lot faster. It had a greater acceleration, okay? So I don't know. This is probably Derek in his Ferrari, and he's going 0 to 100 in 10 seconds. This is Miss Buck over here in her handy little CRV. And I don't even know if my CRV will go to 100, but I got there. I got to the same speed. It just took me a lot longer, okay? So yes, we want you to draw this in and we want you to write these words in your notes. This is a lot, okay? Acceleration is, just write your summary, put down a basic definition. It's a vector quantity. If both acceleration and velocity vectors are pointing in the same direction, tell me what the object's doing. If they're pointing in opposite directions, tell me what it's doing. And then here, the patterns on a speed time graph are different than the patterns on a distance time graph. The patterns on a speed time graph are, just list a couple of them, okay? Just list them out. If you have a flat horizontal line on a speed time graph, that means constant speed, for example, okay? All right, that'll get you started. Don't worry, this takes practice, okay? It takes practice.